Alright, in this video we look at a couple more examples of section 5.3, particularly related to the fundamental theorem of calculus part 1. And so the sequence of ideas here is that a function f of x would probably be given to you. Okay, you could make an attempt at finding that area function. And then once you have an area function, it is a function, you can then move and try to ask what is the derivative of that area function. And you'll find that the derivative of the area function is the original function that you were given at step 1. Okay, so for example, let's go through an example here. We can see on the left side of the screen that we've been given the function f of x is equal to negative x times x minus 3. So here is a function f of x. We can make a new function called the area function and integrate that function from 0 to x, f of z dz, which means that we're going to integrate from 0 to x, find the definite integral of negative z squared plus 3z. Okay? And when you compute that definite integral, it's actually possible to find the antiderivative, capital F of z, and then we will evaluate that from 0 to x. So we will find here that when you find the antiderivative of the integrand, you will get negative 1/3 z cubed plus 3/2 z squared. And then when you evaluate that from 0 to x, you get negative 1/3 x cubed, plugging in x wherever you see the z, plus 3/2 x squared. So here is our area function. Okay, and now moving to the third step, here is the first step, the second step. Moving to the third step, now that you've found an area function, we can take the derivative of it with respect to x. Right? And so the derivative of this known area function is negative 1/3 x cubed plus 3/2 x cubed squared, x squared. That derivative would be negative x squared plus 3x, which is the original function negative x squared plus 3x. So we got back, as promised, to the original function. Okay, what we're seeing in this function, this accumulation, this area problem, is the accumulation function is accumulating area. Okay, so the solid dotted line is the original function f of x given. The area function is getting bigger and bigger and bigger. And right here at 3, we reach a maximum for the area function. And then we can see that what happens after that is that the area will come down because we're starting to get negative area. So we had a maximum for our area function at 3. Okay, and that makes sense because if you want to find where the maximum values of the area function are, you find the derivative of that function and set it equal to 0. But because the derivative of the area function is the original function itself, negative x times x minus 3, when you set the derivative of the area function to 0, we get that x equal to 3 is a critical number of the area function. And so that means that x equals 3 is a location where you have a chance to have a local maximum or minimum of the area function. And we can see from this graph that at 3 we have a local maximum of the area at x is equal to 3. Okay? Now, the reason we're looking at this example again is just to become a little bit more familiar with the 3 different steps. The original function, what it means in terms of area, and then how the derivative of that area function, which is the original function itself, how all those work together. Okay, I want to point out that there are other functions, like this one for example, f of x is equal to e to the negative x squared. Here is also a function that we could try to look at the area function of, e to the negative x squared. Okay, And if you look at this function as the dotted line, it's kind of you can see it's the part as the dotted line here, right? And so when we look at the area function, that would be the definite integral from 0 to x of e to the negative z squared dz. Now, what we won't be able to do is to know what that area function is as a function. We can see here that with the computer, it turns out that that's 1 over square root of pi ERF, something called the error function. And that is kind of a mystery what that function is. But if we acknowledge that we don't really want to know exactly what the area function is, but what is the derivative of the area function, then we will get e to the negative x squared according to the fundamental theorem of calculus part 1. So there are functions out here, functions that are actually accumulation functions, okay, that are new functions that we've never seen before, okay? And one of those new style of functions is something called the error function, okay? So if we had to take the derivative with respect to x of the square root of pi over 2 ERF of x, the error function, that the answer to that would be e to the negative x squared. So this is a new function that we've never seen before, but its derivative is something we've seen before, e to the negative x squared. Okay? So one thing that we're trying to understand here is that a function can be given to you, any given function. For example, that function might actually be a rate of change function. You might have a rate of change function. And what I mean by that is you might be given f prime of x, okay? And then in which case you can find the accumulation function, which is the definite integral from 0 to x of the rate of change function, okay? And this we actually know the answer to. It is the antiderivative of f prime, which is called f of x, f of z dz. It is f of z evaluated from 0 to x, which is f of x minus f of 0. And then if you ask for the derivative of that area function, you would have the derivative with respect to x of f of x minus f of 0. You would get f prime of x. So the same thing happens that we expected. If you start with a function, find its accumulation function, it actually turns out that we can find the answer to that as a specific value, okay, or as a specific function. And then when you take the derivative of it again, you get back to where you started. Okay. So the point here is that notice that the accumulation function has the units of the function itself without the derivative on it. So as an example here, you might be given f prime of x. The function that you're given might be, let's say that this is the function that you're given, might be a velocity function, v of t for velocity. Okay, in which case the velocity is the derivative of the position. So let's say that you're given the velocity graph. You can then find the accumulation function as a function of time would be the definite integral from 0 to t of the derivative of the position, s prime of z dz, right? In which case you would know the answer to that. It would be the function, the position function, minus the position evaluated at 0. And then if you took the derivative of this accumulation function, you would get to the derivative with respect to t, s of t minus s of 0. S of 0 is a number, so its derivative is 0. The derivative of the position function is s prime at t, which is equal to the velocity. Okay, so one thing that we are seeing here is that the original given function might have the units of meter per second, but the accumulation function has the units of meter per second times seconds, which has the units of meter per second times seconds is meters, which is the units of position. And then when you take the derivative of something in meters, the derivative with respect to t will be back again to having the units of meter per second. Okay? So this is a very important problem here, that you're not always given a function that is just devoid of any meaning. Sometimes you're given a function that is a rate of change function. And that rate of change function might be a function that is like infections per year, or it might be the amount of dollars made per year, or it might be the number of change of people per year, so it may be a birth rate. So all of these are examples of given rate of change functions. Okay, so let's say that you're given an f prime of x. If you want to accumulate the f prime of x function, okay, dx, from x going from 0 up to some value, we'll call it t. This would be an accumulation function in t, right? Then this will have the units of, say, the units will be the units without the rate on it. And what I mean by that is if, for example, f prime of x was dollars per year, then dx would have the units of years, and the units without the rate would be dollars per year multiplied by year, which is equal to a dollar amount. Okay, if, for example, that you had f prime of x was the population change, you would maybe have the birth rate, population of people growing per year, multiplied by years, which is this second entry. Then you would have the units of number of people. Okay, so when we're doing a definite integral, the definite integral of a rate of change, the answer is the definite integral of a rate of change has the units of a total amount, so to speak. Okay, so if we are computing a definite integral from 0 up to some amount of time of a velocity graph, velocity f of, let me be careful with the time here, we'll say a new variable tau t, d tau. The velocity is in units of meter per second, d tau time is in seconds. That what we are doing is accumulating, that is the definite integral, we are accumulating velocity times time, which will have the units of an accumulated amount, meter per second times seconds, which will be in meters, which is the units of distance. So this would be related to our position function, which is meters. Okay, so ends this video on the interpretation of a definite integral of a rate of change.